All right, so last night when you did the nth term test and got that the nth term approached 0, we had to stop and say, okay, well, the test is inconclusive. We don't know if the series converges or diverges. So for the next few days, I'm going to introduce new tests for you to use in that case. And this one is called the integral test. And basically what the integral test says is that if you have a series and you basically turn the series into an integral, so you're integrating from the bottom limit to the top limit, which is going to be infinity. If that integral converges, then therefore the series converges. And if the integral diverges, the series diverges. So they either both converge or both diverge. And this is why we had to do those improper integrals in Chapter 8, so that we could determine whether the series diverged or converged using the integral test. All right, so determine whether the series converges or diverges. Still, I want you to always, always, always use the nth term test first, which like you did last night. So the nth term test is the limit as n approaches infinity of that formula that's your series right there. So n over n squared plus 1. So what is that limit? Okay, infinity over infinity, so I could use L'Hopital's rule. So I get 1 on the top and 2n on the bottom. So now the limit as n approaches infinity of 1 over 2n is 0. Okay, and that's great that you use L'Hopital's rule, but don't forget about those horizontal asymptote rules, where since the degree of the top of your original limit was less than the degree of the bottom, that limit should be 0. All right, so because that limit equals 0, the nth term test is inconclusive. This series may converge, it may diverge. So today we're going to use the integral test. So what I'm going to do is I'm going to take this n over n squared plus 1, and I'm going to integrate it between n equals 1 and infinity. But when I flip it over to the integral, the standard notation is to switch to x's instead of n's. And I think it's just to kind of differentiate more between the series and the integral. All right, so we've created an improper integral because of that infinity. So how do we deal with that infinity? Limit as b approaches infinity, integral from 1 to b of x over x squared plus 1 dx. Now, how am I going to integrate that? Okay, a u substitution with x squared plus 1. Where is this kind of going? How am I ultimately going to integrate it? Natural log. Good. And if you recognize that, you can go through the whole u substitution, but if you recognize that it's going to be natural log, if you can just get the derivative of the bottom up on top, which we would need a 2, and therefore a 1/2 out in front, then you could skip the u substitution if you want, or kind of think about doing that in your head. So it's the natural log of the bottom. From 1 to b. Okay, so next step is plug in the b minus plug in the 1. All right, so as b approaches infinity, b squared plus 1 approaches infinity. So what's the natural log of infinity? Infinity, very good. So we have infinity minus that 1/2 natural log of 2, which is just a number, so that's still going to be infinity. So remember that in Chapter 8, we got when the value of the integral equaled infinity, we said that integral diverged. Well, because the integral diverges, the series will also diverge. So our final answer is that the series from n equals 1 to infinity of n over n squared plus 1 diverges. And we're introducing a new test every day here, so I want you to start telling me why, or by what test, so it diverges by the integral test.
Just draw an integral sign and say test.
Okay, so number 2. Always start with the nth term test. And if you can do the nth term test in your head, that's fine. You don't have to write it down, but it will save you some work if you'll get in the habit of always doing that nth term test. So if I were to take the limit as n approaches infinity of 1 over n squared plus 1, what am I going to get? 0. Okay, so the nth term test is inconclusive. Therefore, I'm going to have to do something else. Now, if the nth term test, you get something other than 0 for that limit, then write that down and say it diverges by the nth term test. And then you can move on. But if that nth term test gives you 0, then there's no need to write it down. All right, so I'm going to convert this to an integral. So it would be the integral from n equal, we don't put n's on integrals. We just do the integral from 1 to infinity, 1 over x squared plus 1 dx. So the improper part is going to be limit as b approaches infinity, integral from 1 to b. Okay, been a while since we've integrated that, but very good. Arctan. Is it arctan what? X, just arctan x, any of the other frills or? Okay, just arctan x. So limit as b approaches infinity, arctan x from 1 to b. Plug in your b. So arctan of b minus arctan of 1. All right, what is the arctan of infinity? Pi over 2. Y'all are so good. And the reason for that is there's your graph of arctan x, and your horizontal asymptotes are at pi over 2 and negative pi over 2 there. Okay, and what angle has a tangent of 1? Pi over 4. So pi over 2 minus pi over 4 is pi over 4. So this integral, since the value of that integral is an actual specific number, that integral converges. So since the integral converges, the series also converges. So to kind of sum up the problem, the series 1 over n squared plus 1 converges by the integral test. Okay, the question is, do we need to put what it converges to? And the answer is no, because the sum of the series is actually always greater than the value of the integral. And geometric series that we talked about yesterday are really the only series that you can very quickly and accurately find the exact sum of. The other series will take approximations to find them. So at this point, we just need to say it converges. And it doesn't converge to pi over 4. It's going to converge to something that's a little bit bigger than pi over 4, or maybe a lot, but it's at least something that's bigger than pi over 4. When I'm grading quizzes and tests, pi over 4 is going to be a big part of the points right here, because I want to see that you can accurately evaluate that that improper integral. So I will be checking your work and not just your final answer. So keep that in mind. Okay, determine whether the series 1 over n times ln n converges or diverges. There's a lot of n's in that. Nth term test kind of in your head. What is that nth term approach? 0, right. Limit as n approaches infinity of 1 over n ln n is going to equal 0. So I'm going to try the integral test. And at this point, the only reason I know to use the integral test as opposed to something else is that, one, it's obviously not a geometric series, and the integral test is the only one that we've learned so far. What's my lower limit of integration going to be? 2, right. Your limits of integration are the same as what's on the series. Okay, I'm hearing rumblings of U substitution. So what do you want to let U be? Good, ln x. I kind of go over here and work on the actual integration. All right, so U equals ln x. So du is 1 over x dx. So I'm integrating 1 over u du. And the integral of 1 over u is natural log of u. But u was ln x. So it's the natural log of the natural log of x. Oh, this should be a 2. Yeah, it is supposed to be absolute value, and I was actually trying to make this an absolute value, but it kind of looked like a parenthesis. Oh, the x does not have to be an absolute value because this ln x right here was a part of the original problem. And if it's part of the original problem, you don't have to add any absolute values. Okay, so plug in my b minus plug in the 2. And what does that limit equal? Infinity, right? And the reason that the natural log of infinity is because of the graph of ln x. As x approaches infinity, natural log of x approaches infinity. So this diverges by the integral test. All right, p-series. You're going to hear a lot about p-series, and that's good because they're very simple, easy to recognize, and easy to deal with. So a series that's in the form of the sum of 1 over n to the p, which would be like 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, is called a p-series, and p is a positive constant. So like 1 over n squared, 1 over n to the 5th, that's a p-series. 4 and 5 are both examples of p-series down there. For p equal 1, that's a very special series, and it's called the harmonic series. And the reason that it's called a harmonic series is because it's the parent function of 1 over a n plus b, where a and b are just constants. And in music, strings of the same material, diameter, and tension whose lengths form a harmonic series produce harmonic tones. So if you've ever heard about harmony or that any form of harmony or harmonic in terms of music, then that's what creates those tones. So math and music are actually fairly closely related in a lot of aspects. All right, so we're going to use the integral test to determine whether the series converges or diverges. So 1 over n to the 1/2 and 1 over n cubed. I would like for you to just kind of either with one other person or by yourself use the integral test with both of those series to figure out whether they converge or diverge.